Okay, so we alluded to this last time when we were doing solution stoichiometry on Wednesday. I told you that the next thing that we will do is limiting reagent solution stoichiometry, right? Because on Wednesday when we were doing our calculations, you notice that all the problems said excess, right? Anytime you see that word excess, that means that one of those reagents you got a lot of, right? You're not in any danger of it being the substance you run out of first. But if you've got limited quantity of both substances, right, now you've got that information, that means you do a different kind of calculation. So anytime you know information about more than one substance, and I say substance because it could be a reactant or it could be a product, okay? So that's why I use the word substance and not the word reactant, because you could have a reaction, I mean, you could have information about one reactant and one product. Those are two substances, okay? So don't let it confuse you. Anytime you know information about two substances, could be a reactant, could be a product, okay? That's limiting reagent, which means you're gonna do the stoichiometry twice, just like when we did regular stoichiometry, quote unquote, regular stoichiometry, right? We did our stoichiometry 2 times, and then we compared, and then the smaller value was the answer that we chose as our theoretical yield. We're gonna do the exact same thing when we're doing solution stoichiometry involving limiting reagent. We're gonna pick the smaller value. So let's do this one together. A 450 milliliter sample of 0.52 molar calcium chloride reacts with 125 milliliters of 0.78 molar potassium hydroxide. What mass of precipitate is formed? Okay, so we're reading this problem. Let's break it down, make sure everybody sees what's going on. We know the volume and molarity of solution number 1, and we know the volume and molarity of solution number 2, right? So we know how to get moles for 2 substances, right? Because think back to last time we did this on Wednesday. How do we get moles if you know molarity and volume? Well, moles over liters is molarity, therefore moles is molarity times volume. But volume must be in liters, right? So as I mentioned on Wednesday, you always want to get in the habit of converting milliliters to liters before you're doing any calculations, right? Move that decimal 3 to the left. Before you begin, build that into your practice so that way you don't forget to convert milliliters to liters. Because milliliters times molarity will give you millimoles, which is not what we're looking to do here. Does everybody understand why this is limiting reagent? You know molarity and volume for 2 substances. If you know information about 2 substances, then you've got to do the stoichiometry for the precipitate for this one and for this one, okay? You can't do it just once, you've got to do it twice because we know information about both substances. Now here, both substances are reactants, but it's not going to be the case always. So let's do this one first. We have to write a balanced equation, right? And then again, list what you know underneath that substance. CaCl2 plus 2 KOH produces CaOH2, that's our precipitate. How did I know that this was the precipitate instead of this? How did I know that calcium hydroxide was the precipitate? What did I use? Well, I didn't use anything because I already know my solubility rules, but you, what would you use? Your solubility rules, right? After you start doing this long enough, you'll start committing those to memory. But for now, pull out your solubility rules or turn in your textbook to your solubility rules. That's what we use to tell us that this is the precipitate. This one is soluble, okay? Potassium chloride soluble. It's just hanging out in the solution. We're not interested in it at all. This is our precipitate. It's going to sink to the bottom of my test tube. White precipitate down there at the bottom. It'll be very easy to see, okay? This is the precipitate we're interested in. We want to know what's the theoretical yield of that precipitate, given this molarity and volume and this molarity and volume, okay? Again, like I said, because we know information about both substances here, we have to do limiting reagents, okay? We have to figure out which substance am I running out of first. So we're going to do the stoichiometry going from here to here, and then from here to here. And then the smaller value is the answer that I pick as my theoretical yield. Does this make sense? Everybody good? Any questions before we get into the calculations? Okay, so let's do the calculations. We're going to do it twice. All right, I'm going to start with calcium chloride because it was first on the list. So step 1, we're going to convert our molarity and our volume into moles, right? Volume times molarity gives me moles, because liters cancels. So 0.45 times 0.52 gives me 0.234, right? Liters cancels, so that's how I'm left with moles. Molarity times volume, or volume times molarity is the same thing, right? Volume times molarity. You could have listed molarity times volume. Either way, liters cancel. You're left with units of moles. So that's step one. Now, what's step two? What do I do second? Right, the coefficient step, the mole ratio step. Now here the mole ratio is 1 to 1. Right, so my number isn't going to change. However, my units are changing. Right? For every 1 mole of calcium chloride that I use, I produce 1 mole of calcium hydroxide. So my number doesn't change because I'm multiplying by 1 and dividing by 1. Right? My number isn't changing, but my units are. Okay? So how did I convert from moles of calcium chloride to moles of calcium hydroxide? Multiply by the mole ratio. So just remember, you should show that step. Even if it doesn't change your number, I still need to know how you converted from one unit to the other, okay? I want to know that you know what you're doing. And then last, the problem asks for the mass of precipitate, not the number of moles of precipitate. So I convert that to grams, rounded my molar mass to 73. I can keep, not 3 sig figs, 2 sig figs, right? Because that molarity only has 2 sig figs. So it's not 17.1, it's just 17. Right? Because that's got 2 sig figs, that's got 3. So I can only keep 2 sig figs in my final answer. Do we agree on this process? This is exactly what we did on Wednesday. Right? This is identical to what we did Wednesday. So not anything new. We're just going to have to do it again. Right? We've got to do this whole process again because we know information about my other solution. On Wednesday, I would have said excess, right? But today, I know exact quantities of both substances, so now I've got to do it twice. Step 3 didn't hide like I wanted it to. Oh well. So the first thing we're going to do is we're going to convert to moles. Right? Volume times molarity gives me moles. So liters cancel, so I'm left with units of moles. We're carrying out extra digits because we're going to be rounding at the end. Right? So step 1, molarity times volume gives you moles. Step 2 is the mole ratio step. This time it's a 2 to 1 mole ratio, right? For every 2 moles of potassium hydroxide I use, I produce 1 mole of calcium hydroxide. So we have to factor that in. Coefficient of 2 now on the bottom, so we're dividing by 2 this time. And then step 3 is the same as it was in the last problem because the molar mass of calcium hydroxide hasn't changed. So we're just converting moles to grams using molar mass. And let's see, I've got too many sig figs again because that's 2 sig figs. So that should be 3.6. Right, because I can only keep 2 sig figs. Does everybody agree on this process? How we got these values? Now you can do this all as one step, okay? I'm perfectly fine with that. As long as you understand how to do it as 3 individual calculations, I am perfectly fine with you doing it all in one calculation. Makes no difference to me which way you do it. Okay, you're going to get the same answers either way. But I only recommend doing it all as one big long calculation when you feel really comfortable with them individually. Okay, 3 individual calculations, if that makes sense to you and you're good, then you can smash them all together into one big long one. But I would not recommend doing that until you are confident in setting up each individual step. Do we agree here? Now we're just going to compare. Again, I've got too many sig figs, but that's okay. 17. You can always round at the end, right? My little text box is in the wrong spot because I was rounding poorly. Right. 2 sig figs can be retained, not 3. So the calcium chloride gives me 17 grams of precipitate. PPT just stands for precipitate. And the potassium hydroxide gives me 3.6 grams of precipitate. That means that the potassium hydroxide is my limiting reagent, right? This little symbol means therefore. You math whizzes in the audience, right? That means therefore. Therefore, potassium hydroxide is my limiting reagent, and therefore the theoretical yield would be 3.6 grams, not 17. All right, you pick the smaller value as your theoretical yield, and the substance that produced that theoretical yield is the limiting reagent. What do we say that calcium chloride is? If one is limiting reagent, what's the other one called? We use this word on Wednesday. Excess, right? Okay, so you pick the smaller value as your theoretical yield. Theoretical yield comes from the limiting reagents, stoichiometry. Does this make sense? Okay, you do this one. What mass of precipitate is produced when 76.89 milliliters of a 5 molar lithium sulfate solution is combined with 81.46 milliliters of a 6 molar barium chloride solution? I'll pause the recording while you tackle this one. The answer to this problem, this is limiting reagent because I know molarity and volume for both of my reactants, right? So I'm going to have to first figure out which substance is my precipitate. What is the precipitate? What's the identity of the precipitate? Right, barium sulfate is the precipitate. So I have to write my balanced equation, and then I have to identify who's the precipitate. And now it's a limiting reagent calculation, right? So I did it as one big long calculation. Right, here is volume times molarity, so liters cancel. Now I'm in moles of lithium sulfate. Here's mole ratio, so 1 mole lithium sulfate for 1 mole barium sulfate, so lithium sulfate moles cancel out. Here's converting moles to grams, right? So if I multiply straight across and divide up, 0.07689 times 5 times 233.4 divided by 1 times 1 times 1, right? 3 significant figures can be kept. Now, if you did it as 3 separate calculations, that's perfectly fine, okay? I'm just putting it all as one, just so you can see what that looks like. But if you're doing it as 3 steps, you would do this calculation, volume times molarity, take that number, then you do the mole ratio step, which wouldn't change the number, it would just change the units. Take that number and then convert to grams. We're going to do it again for my second substance, the barium chloride. Again, doing it as one big long calculation. Right, here's volume times molarity, so we're left with moles of barium chloride. Mole ratio here is also 1 to 1, so numbers do not change, only units. So barium chloride moles cancel. Now I'm in moles of barium sulfate, but I want to know grams of barium sulfate, so I multiply by the molar mass, which is the same as it is up here. Right, you want to calculate that molar mass once. 3 significant figures. So now I compare 89.7 versus 114. So 89.7 is my theoretical yield, which means that lithium sulfate was my limiting reagent. So if you're comfortable doing it like this as one big long calculation, go for it, right? I have no problems if you do that. It saves you some writing. But if you're looking at this and you're like, whoa, that's a lot of conversion factors all smashed together once, then don't do it this way, okay? You're not required to do it as one calculation. It's perfectly fine to split it up into 3 steps, okay? That's perfectly fine, and if that's what makes sense to you, then that's what I want you to do, okay? Don't try to do something that doesn't make sense. If 3 steps make sense and one big long calculation doesn't, then you can do the 3 steps. That's fine. I always give you plenty of room to write on quizzes and tests so that you can do it as 3 steps if you want to. All right, let's do this one. When zinc metal reacts with hydrochloric acid, hydrogen gas and zinc 2 chloride are formed. What mass of hydrogen gas is produced when a 4.68 gram piece of zinc metal reacts with 754 milliliters of 5.25 molar HCl? Think about what kind of reaction this is and do some calculations. Let me pause the recording real quick. Okay, let's look at the solution this time. What kind of reaction is this? Single displacement, right? This is single displacement because we've got a metal and a compound, right? So hydrogen gas, is that H or H2? H2, right. Would zinc 2 chloride be a precipitate or would it be aqueous? That one's aqueous, right. So there's our balanced equation. We've got mass of the metal and we've got molarity and volume of the solution. And we want to know how much gas this will generate. We're not interested in the solution at all. So here's what it looks like if you do it all as one calculation. If you did it as 3 separate calculations, that's perfectly fine. Right? Converting grams to moles, right? That's just the molar mass. Mole ratio is 1 to 1, so numbers do not change, only units change. And then the mass of H2 would be 2.016 grams per mole. So when I multiply straight across, 4.68 times 1 times 1 times 2.016 divided by 65.38 times 1 times 1. So, keeping 3 significant figures, my mass is 0.144 grams of H2. Do we all agree on the zinc calculation? Does the zinc calculation make sense? Grams to moles, mole ratio, moles to grams. Right? So that's pretty much, that's regular stoichiometry. Right? I mean, that's exactly what we did. There was no molarity or volume involved in this calculation at all. That's just regular stoichiometry. And then there's the calculation for hydrochloric acid. I've got a molarity and a volume here. Right? Don't forget to convert milliliters to liters. So volume times molarity gets rid of liters. That gives me moles. Mole ratio here is 2 to 1. Right? So 2 moles of HCl used for every 1 mole of H2 that's produced. And then now my last step, converting moles to grams, cancels out moles, gives me grams. Now I compare which mass is the theoretical yield, 3.99 or 0.144? The bigger number or the smaller number? Smaller number. Do we agree on these 2 numbers? Did you get the same thing I got? Within rounding? Do we agree on the calculation? So the theoretical yield would be 0.144 grams. Are we all in agreement here? Yes, no, maybe? Ready to try a different kind of problem? Shake stuff up a little bit. Okay, try this one. You combine a 1.50 gram piece of copper metal with 100 milliliters of a silver 1 nitrate solution of unknown concentration. Whoops. The stock person forgot to label the concentration on the bottle. My bad. The mass of the solid that forms is 1.84 grams, and the resulting solution is blue in color. What was the concentration of the unknown solution? I think the problem will help you deduce what the equation should be. Pause the recording. All right, let's see the solution here. Have you done this reaction before? Have you seen it? Yes, we've done this exact reaction, right? We've done this kind of reaction. What kind is it? Single displacement, right? Copper metal and silver 1 nitrate. What is the solid that forms? What is that? Silver metal, right? And the resulting solution has what formula? What is the name of it? Let's rephrase it. Copper 2 nitrate, right? Right. So we did this experiment ourselves. Now here we're solving for molarity, right? We want to know the molarity of the AgNO3. So how could I go about doing that? Well, I know the mass of this piece of metal, and I know the mass of this piece of metal. So it's limiting reagent, right? I have to go back calculate what number of moles of AgNO3 could be produced from this mass, and then back calculate here what number of moles of AgNO3 could be produced from this mass, right? And then I pick the smaller number, Once I know moles, moles over liters would give me molarity, right? So there's the calculation for our copper. Grams to moles. And then now all you have to do is mole ratio, right? Because we want number of moles. Don't keep converting. Don't go all the way to grams. That's unnecessary, right? Because the formula for molarity is moles over liters, not grams over liters. So if you went all the way to grams, you did a step too far, right? You don't need to do that because all you need is moles so that you can calculate molarity as moles per liter. Does everybody see why you don't need to calculate it out all the way to grams? Right? That's unnecessary work because you're going to have to convert grams back to moles before you turn it into a molarity anyway. So that's what I got for copper. That's what I got for silver. Grams to moles, mole ratio here is 2 to 2. So I got 0.0176, 0.01706 versus 0.04721. Pick the smaller number. Which is smaller, 0.01 or 0.04, right? 0.01 is my smaller number. Therefore, molarity is moles over liters. So I use my smaller number of moles and I divide it by my 100 milliliter sample, right? So 0.1 liters. And then keeping 3 significant figures, I got 0.171 molar. Did you? Are we in agreement? Does everybody see why you stop at moles this time? You don't need to calculate it out all the way to grams because we're not asking for what mass of solute is dissolved, right? We're not asking that. We're asked what's the molarity. So the molarity is calculated using moles. So in your solution stoichiometry, you actually only have to do 2 steps instead of 3. Woo! Does this make sense? Using the masses of the 2 solids, we calculate the molarity of the unknown. Is everybody cool on this one? Okay, do this one. 125 milliliters of a 0.4 molar sodium sulfate solution is added to 350 milliliters of a lead 2 iodide solution and 0.0011 grams of lead 2 sulfate precipitate forms. Wow, that was so nice. I even identified the precipitate form. What was the concentration of the original solution? And then, what was the concentration of iodide ions in the original solution? I think if you can figure out A, you can figure out B. I'll give you a few minutes to think about this. All right, last one. So we know that we have a precipitate, right? Because I tell you, and I even identified it for you. I was really feeling nice. And we know the molarity and volume of one of the solutions, but we don't know the molarity of the other solution. Right? So because we know information about 2 substances, this is limiting reagent. So first of all, we want to figure out what's the concentration in the first solution. All right, so here we go. Sodium sulfate and lead 2 iodide producing lead 2 sulfate and sodium iodide, right? And we are going to do calculation going this direction. We're going to do calculation going this direction. And I'm just noticing something. Lead 2 iodide is actually insoluble. That's definitely a precipitate. But let's just pretend, for the sake of argument, that this is soluble. But lead 2 iodide is actually insoluble. It's a bright yellow precipitate, but let's just pretend. Hey, let's pretend that this is soluble. All right, so we're going to do the calculations going this direction, right? Molarity times volume, or excuse me, volume times molarity is the way I've got it here, right? These volumes cancel, we're left with moles. And then the mole ratio is 1 to 1. We do not have to go all the way out to grams, right? Why? Because I'm trying to figure out molarity, yes? Molarity is moles per liter. So if I calculate it out all the way to grams, I've done extra work that I don't need to do. Because I'm going to have to convert those grams back to moles. And then there's my solid precipitate. Right? So we're converting grams to moles, and then the mole ratio is 1 to 1. So 3.63 times 10 to the negative 6th. Very small number compared to 0.05, right? Therefore, this is my number of moles. right? Do we agree there? Now again, we're pretending that PBI2 is soluble. It actually isn't. We're just pretending that it is. That was a gross oversight on my part. That's okay. Teachers make mistakes too. Now, is this my final answer? Is that the final answer? No, the final answer is to calculate molarity, right? So molarity is moles per liter. So molarity is moles per liter. So that's what I got. And then how would I get the iodide ion concentration? Well, again, we're pretending that this dissolves. It actually doesn't. It's pretty insoluble. But let's just pretend, for the sake of argument, that it is soluble, right? If this dissolves, for every 1 lead-2, I get 2 iodides, right? So if I want to know how much iodide I had, it's just 2 times whatever the molarity is. So the concentration of iodide is 2.07 times 10 to the negative 5th. Concentration of this PBI2 will be 1.04 times 10 to the negative 5th. Units are molarity for both. Does this one make sense? I believe on your homework on this, there's one, obviously not using an insoluble substance, but it's asking for concentration of ion, of a particular ion, right? So you would just multiply 2 times whatever the molarity is, because every time this breaks down, you get 2 iodides. Does this make sense? Okay. So that's where we're going to stop for today. Hope you have a great weekend, nice 3-day weekend, and I will see you next week.